Okay, I knew where we are here. So in my first talk, I mainly explained why quantum gravity is hard, or in particular why canonical quantum gravity is hard. And I sketched how people had tried to do it in the 60s and 70s. I explained the formulation of Einstein's equations as an initial value problem and described the phase space of solutions of Einstein's equation modulo diffeomorphisms. And I sketched what you would be trying to do to quantize such a thing. And in particular, one of the things you might like to do would be define L2 of the space of all metrics on the three-manifold representing space. But we have no clue as to how to define L2 of the space of metrics. Then in the second talk, I showed how we can define L2 of a space of connections. Connections where your gauge group is compact. And the trick we used was to first study gauge theory just on a graph, where a connection amounts to giving a holonomy for each edge of the graph. So then your space of connections is just some finite product of copies of this compact group, and we all know how to do integrals on that kind of thing. And so from there, we can take a kind of limit construction, inverse limit construction, to define a space A bar of which contains the connections on a real analytic manifold, and we could get a measure on there and define L2 of the space of connections that way. So now what I want to do is bring these two ideas together. So I want to show how we can formulate Einstein's equations in terms of a connection, so that now what we really want is L2 of the space of connections as our so-called kinematical Hilbert space, the Hilbert space you start out with before you impose these constraints, which include 4 of Einstein's equations. And then what I'll do is I'll describe in those terms some interesting operators that you can define on the Hilbert space you get. So the idea is that if you're really trying to talk about general relativity, you're trying to talk about geometry. Here, since we're doing canonical quantum gravity, we're mainly talking at first about the geometry of space. And so there should be operators which talk about the geometry of space, and I'll talk mainly about area operators and measure the area of a surface in space. And these area operators will turn out to have discrete spectrum, and they'll also turn out not to commute with each other. So let me get going on that. So first I have to explain how you can write Einstein's equations in terms of a connection. So this way of rewriting Einstein's equations is still often called the new variables, or sometimes the Ashtekar variables, although it was discovered not so recently anymore, around 83 by Ashtekar. There's going to be some geometry in here of the sort, it's just differential geometry, but it's of the sort that I think people in general relativity are infinitely more comfortable with than most of the mathematicians I've met. People in general relativity have names for all sorts of bundles that they like to use, and names for sections of these bundles. I'll resist using that terminology because I've found that when I try to talk that way to mathematicians, it just doesn't seem to work. They like to talk about cotetrad fields and densitized cotetrad fields and frame fields and co-frame fields and things like that, and internal spaces. And it's all good stuff that differential geometers should know about, but I'll try to avoid as much of that terminology as I can. But even if you don't understand what I'm saying there, we can just skip over that section and wait for the fun part, which is when the operators on this Hilbert space come in. Okay, so the old approach is to use as your kinematical phase space for general relativity the cotangent bundle of the space of metrics on the three-manifold. Kinematical means that we haven't imposed the constraints yet. So a point in there, remember, consisted of a metric on your three-manifold together with this cotangent vector, which gave you information about the extrinsic curvature of the three-manifold as it sits in the four-manifold, which will be our solution for a Lorentzian four-manifold, which will be our solution of general relativity. So S is going to be a compact-oriented three-manifold here. So we're not going to do that anymore. Instead, we're going to take as our kinematical phase space the cotangent bundle of the space of connections. Connections on what bundle? Well, on the spin bundle of our three-manifold. If you have an oriented three-manifold, you can always find a spin structure for it. And so that will be a principal SU2 bundle. So how do we relate this new idea to the old one? Let me sketch that. Here's where the somewhat sneaky geometry comes in. So I need to explain to you the meaning of these new variables, the connection and the cotangent vector to the space of connections. I'll explain their meaning by telling you how they are supposed to relate to the old variables, the metric and the extrinsic curvature.
Can I ask a question?
Yep.
Why don't we use SO3, which would be more natural for...
You can do that too. The reason why I'm going to use SU2 is mainly because if later on in the day we wanted to bring spin 1/2 particles like electrons and so on into our theory, then we would need to have a connection on the spinor bundle to know what to do to differentiate them. But right now, actually for everything I'm doing, you could use SO3 as well as SU2. Some answers would change. Classically, the theories would be the same for what I'm doing. But interestingly, at the quantum mechanical level, even in the absence of spin 1/2 particles, you get some different results. But it's an interesting issue. So the connection, this connection on the spin bundle, is given as follows. It's a difference of two things. First, we take the connection on the spin bundle, which is associated to our metric on the three-manifold. So the metric gives a Levi-Civita connection, and then if you have a spin structure, that you can promote that to a connection on the spin bundle. So that's what I'm calling gamma here. And then, of course, if you have a connection, you can get a new connection by adding to it any Lie algebra valued one form, or more precisely, any one form, taking in the values in this bundle, the adjoint bundle of our principal bundle. So this is the associated bundle where we use the adjoint representation of our group on its Lie algebra. So what we're going to do is we're going to add an add p valued one form to this spin connection, subtract it actually, and we're going to cook up that one form from the extrinsic curvature in a certain way. Let's not worry about this formula too much right now. I'll tell you more about it in a second. But the point is, this connection contains information, sort of a mixture of information, both about the spin connection, or in other words, just a Levi-Civita connection on your three-manifold, together with the extrinsic curvature. They're getting mixed up in this way. To continue on, I have to sort of bring in the second actor here. So that's this E field, which is the cotangent vector. So we're thinking of it as a cotangent vector to a certain point in the space of connections, a certain point A. So what is that like? Well, here we have to think of it. So remember, a tangent vector to the space of connections is, as I just said, it's an add p-valued one form. So I'm using somewhat lousy notation here. I don't really like this notation, but I sort of screwed up. But what I mean here is that we're taking the space of add p-valued one forms, and that's our tangent space to the space of connections. So then the cotangent space to a point in the space of connections will just be the dual of this vector space. So what's the dual of this vector space going to be like? Well, we can think of it as two separate problems. What's the dual of this fiber like? Well, that will just be the dual of a fiber. And what's the dual to the space of one forms like? Well, the dual to the space of one forms on a manifold, we're on a three manifold, okay? So the dual to the space of one forms on a manifold, naively, you might think it would be the space of vector fields. But that's not quite right, because if you take a one form and a vector field, you can pair them and get a function. But to get a number, you have to integrate that function. So you can't do that in an invariant way unless you have a volume form around. So the real answer to the dual of the space of one forms is this. It's the space of vector fields tensored with the space of three forms, or in other words, densities. Here, this is why it's lousy notation. Here I'm tensoring over the space of smooth functions. So the dual to the space of one forms is what physicists would call the space of densitized vector fields. That's something that all physicists, all general relativity people know about, but it's just this, it's this thing together with this thing. Okay, so to bring in a little more of this terminology, sections of this, or elements of this, are often called frame fields because what they are doing, a way to think of what they're doing is if you give me any vector in the fiber of add P, it spits out a tangent vector. So if the bundle is trivial, a section of this thing is simply a gadget that if at any point in space you give me a vector in R3, it will give you a tangent vector. And that's just a frame, or a triple of vectors at each point. Okay, so...
But what is giving a tangent vector? Can you explain how that's
Okay, I was trying to explain the role of... Okay, I'm just leading it. I'll say it again. Yeah. So I'm trying to explain what this little piece here is, and I'm saying, if you give me an element of this, so that's a section of the bundle of tangent vectors tensored with this add P star bundle. If you give me a section of that, and you give me at any point in space a vector in this fiber of add P, it will give to you a tangent vector in a linear way. So if this bundle is trivial, then we can just say, if you give me at any point in space an element of R3, this is a three-dimensional bundle, it will give you a vector. So that's what we call a frame. At least if it's non-degenerate, we call it a frame. It's a triple of vectors at every point in space. So these guys here are called frame fields. They're just what mathematicians since Cartan have been calling frame fields. And I guess what this whole shebang gets called is densitized frame fields. So, okay. So E is a densitized frame field. Okay, but how does it relate to the old language of metric and extrinsic curvature? Well, there's a nice way that's been used for a long time in physics of getting metrics from frame fields. If I'm using some indices to describe this, you can also describe it in a more invariant way. If you give me a frame field, that's a thing that eats vectors in, let's see, I'm sorry, I left out the star here. There's a star there, okay? So a frame field is a thing that eats vectors in a fiber of add P and spits out tangent vectors. So those are those two indices there. If you give me two such things, I can construct a metric. So basically that's just the metric for which that frame field is an orthonormal frame field. So frame fields give you metrics. Densitized frame fields can be related to metrics as well. So this densitized frame field, given a frame field, E, we can cook up a densitized frame field just by tensoring with the volume form associated to this metric. Now let me try to say this over again. I knew this is going to get a little tangly. So suppose you give me a metric on a three-manifold. Then I can pick an orthonormal frame field, and I can do it in many different ways. Call that little e. I can tensor it with a volume form, and that will give me this big E. Of course, that was a non-unique construction. There would be many of these big E's which would be associated to any particular metric on space. So we've introduced some redundancy in our description of the metric when we've switched to working with this densitized frame field instead of the metric. But that's okay. I mean, we'll take care of that later. So finally, to go back here, once you have this, having the frame field is basically the same as having the densitized frame field. You can go back and forth between them. So once we have big E, we can turn the extrinsic curvature into an add p-value 1 form using it in this formula, using this formula here. And that's what we really mean by this. Okay, so it's some fancy, well, it's not all that fancy. It's just some slightly unusual geometry to express the information of a metric and extrinsic curvature in terms of a cotangent vector to the space of SU2 connections. When Ashtekar first came up with this, he put an I here. He put a factor of I here. That's why there's that big blank there. And that's actually a geometrically very natural thing to do because it has to do with duality. Hodge duality for Lorentzian metrics works in such a way that it's very nice to stick an I there. But when you stick an I there, you don't get an SU2 connection. You get an SL2C connection. SL2C is not a compact group, and so we couldn't use all the wonderful machinery that I developed last time. So at some point later on, Fernando Barbero decided to get rid of the I, work with this slightly less geometrically natural connection here, but which has the advantage of being an SU2 connection. When Barbero did that, he noticed that without really hurting anything, you could also make the construction a little bit more general by sticking in any old real number, non-zero real number, gamma, in there. And it works out best, as we'll see, if you also, sorry, you probably can't see both of these things at once. And it works out best if you also stick a 1 over gamma in front of the E. We'll see that then things work out nicest.
These new variables, are they the same number of parameters?
No, they're a bit more because, as I said, lots of different frame fields map to the same metric. I'll describe the map in a minute, which relates this space, the cotangent bundle of A, to the old space, the cotangent bundle of the space of metrics. So we'll see what's exactly getting lost when you map down that way. Yeah?
Aren't we also including, when we switch over to the frame, possibilities of moving out of space where this connection might not, come from one that had was Riemannian, since it might have some torsion now or something, or is that automatically there? If you just add the K there.
Right. What it'll work out, the way it will work out is that you can write down some equations that imply, you can write some equations down in terms of these variables, which imply Einstein's equations. And part of what those equations tell you is that the connection is gamma is torsion-free. I'm not going to go into all those details, but it's very, you really need to do that to really fully understand this. You need to see how can I write down Einstein's equations using these new variables, and why does everything wind up working? Why does, starting from that other viewpoint, why does it work out that we get this torsion-free connection that's metric preserving, and that this is the extrinsic curvature, and so on. Yeah, so that's a somewhat lengthy exercise.
A is a connection on a bundle associated with this connection.
Yeah, it's a connection on the spin bundle. It's an principal SU2
Which
bundle.
spin bundle associated with that connection?
Yeah, that spin bundle, sorry.
And E is what?
E is a cotangent vector to the space of such connections. And I interpreted it in lots of different ways here. So this parameter gamma that you can throw in here doesn't make any difference when you're doing classical work, when you're studying classical general relativity. And so actually at the time Barbero said, well, if you might as well just set it equal to 1 if you like. But then much later on, when people were studying quantum gravity, they noticed that it does make a difference in quantum gravity, and we'll see that it makes a very important difference. That important difference was pointed out by Imirzi, and so people started calling it the Imirzi parameter. I think it's better called something like the Barbero-Imirzi parameter. We'll see that it plays an important role later on, but don't worry about it yet. Okay, so let me say a little bit more about the relation between this way of looking at general relativity and the old one that I talked about before. So, first of all, this is a symplectic manifold, this cotangent bundle of the space of connections. So it has Poisson brackets on it. You can write down the usual physics-style formula for these Poisson brackets. So what this is saying is, physics jargon is that these are canonically conjugate. Their Poisson bracket is 0 unless all the indices match and x and y are the same point. Of course, you need to smear this with test functions to get something well defined. And so if you've studied some physics of this sort, you should think of this as highly reminiscent of electromagnetism, where there are also fields called E and A, in which E is the electric field, A is the vector potential, the thing whose curl is the magnetic field. In electromagnetism, they satisfy similar Poisson bracket relations. And so part of why this formalism is so nice is that it makes general relativity look a lot more like electromagnetism, or more generally, a lot more like a Yang-Mills theory, SU2 Yang-Mills theory. So in all Yang-Mills theories, you have this analog of the electric field and the vector potential, which is just the connection, satisfying these relations. Okay, so as I...
But isn't that a minor bonus because, these are connections on a bundle that lives on the manifold, not an abstract one like electromagnetism. You have to pay, you have to acknowledge that. That's the crucial point.
Well, that's true. It's a trivial bundle.
It doesn't matter. It's tied to the manifold. Okay.
You can just interpret it as an abstract trivial bundle if you'd like, and it actually doesn't hurt.
Then you can throw out the baby if you want.
Well, okay. Keep it tied to the manifold then. We don't want to throw the baby out with that. So there are some maps which are Poisson maps. So last time I said what a Poisson manifold is, so if you're truly categorically inclined, you'll immediately know what a Poisson map is, but if you're not, well, I'll just say a map between manifolds is a Poisson map if you can either take the Poisson brackets of functions over here and then pull back the result, or pull them back and compute the Poisson brackets over here, and you get the same thing. So that's the right kind of map between Poisson manifolds. So in other words, that's the right kind of map between spaces that you'd use to describe states in a classical physics problem. And here we've got a bunch of them. So first of all, there is this one here, which is really an example of this Poisson reduction, going from the cotangent bundle of the space of connections down to the cotangent bundle of the space of connections mod gauge transformations. These gauge transformations, what they have the effect of doing is taking this E field, this densitized frame field, and rotating it around at each point. And so they do not affect the metric which is associated to that E field. We also have a map from our good old space, the cotangent bundle of the space of metrics, down to here. So a metric does not determine a frame field, but it determines a frame field up to these rotations. So you get this map going this way. It's only a densely defined map, which is an interesting... Sorry, it's an everywhere defined map, but its range is only dense. And the reason why I'll explain in just a second. So you define these maps, as I said, by Poisson reduction going down, and by the relations that I wrote down on the last transparency between the A and E and the Q and P going across here. So it's interesting to see why this space is a tiny bit bigger than this space. It's because if you try to define the inverse, well, it's not defined everywhere, and the reason why is it's only defined for pairs A and E, such that E defines a non-degenerate metric. This formula is just the formula that relates the densitized frame field to the metric. It's a consequence of the formulas I wrote on the previous page. Probably shouldn't be dropping all these formulas on you, but the main point is that if this E field, which is a section of some vector bundle, if it happens to be 0, you're not going to get a Riemannian metric out of it. You'll get a degenerate metric, right? A degenerate inverse metric, actually. So the interesting thing about this formalism is that it's really taking general relativity and it's extending it a little bit to allow these inverse metrics, which are degenerate. See, one of the many reasons why quantum gravity is hard, another one, besides all the ones I listed, is that in most field theories, your fields are sections of vector bundles, and you can add two fields and get a new field. But you can't add two metrics always and get another metric. Or, well, you certainly can't subtract two Riemannian metrics and get a metric. Metrics have this inequality condition, this non-degeneracy condition, and the positive definite condition, which are very different than all other fields, and that's a nuisance in quantization. And what we're doing here is we're getting rid of that problem by working with this E field instead of the metric. So when the E field is non-degenerate, it defines a metric. That is, when it's an isomorphism, it defines a metric. But if it's degenerate, our setup will still work, and we're extending Einstein's equations a bit.
So,
Sure.
so can you kind of think, I mean, you said explicitly that you want to take it from it. So can you think of A like a connection on some abstract bundle, and E is providing a bundle map connection with the manifold?
Yeah.
So this bundle map might be non-degenerate or might not.
Yeah, that's another way to set it up, which is actually how people often do, which is better in some sense. Right.
Did you say what they just said?
That's what's hot.
What he's saying? He's saying, can you think of E? Can you think of our P? It's not quite the spin bundle associated to the tangent bundle, but just some abstract bundle, and think of E as a map which links that up to the tangent bundle. And that's a way to do it, which is widely done. And when physicists talk about internal space, that's what they're doing. Yeah.
Is the metric automatically by signature?
Yeah.
Connection on an abstract bundle is just ordinary gauge theory thing.
Yeah.
And this connection, this E is what connects to the manifold.
Yeah, this frame field E is connecting it up to that. Yeah, that's a nuance which is important, but I tried to avoid. Yes. Okay. So that's it for the, well, no, not quite. It's almost it for the differential geometry. So how do we get the physical phase space, that is the space of solutions of Einstein's equations mod diffeomorphisms, from this setup? Well, we have to pay a price. We sort of went back a little further, so now we have to do Poisson reduction 3 times to get down to the physical phase space. It's a bit like backing up before you're going to try to make a long jump. So we start with the cotangent bundle of the space of connections. There are certain constraints that the E field needs to satisfy, which roughly speaking say that its divergence is 0. Those constraints generate a group action, which is just the action of the gauge group, G, on this space. And so if we do Poisson reduction with respect to those constraints, it turns out that we get the cotangent bundle of the space of connections mod gauge transformations. And as I said on the last transparency, that's just a little bit bigger than the cotangent bundle of the space of metrics. This is dense in here. So then, from then on, it works a lot like the old setup. In other words, we have a diffeomorphism constraint to deal with, which is 3 of Einstein's equations, and a Hamiltonian constraint, which is a 4th. And the diffeomorphism constraint generates diffeomorphisms of the manifold S space. And so when you do Poisson reduction by that, what you really wind up with is a cotangent bundle of the space of connections mod all bundle automorphisms. That is, bundle automorphisms that may move the points on the base around. That bundle is actually a semi-direct product of the diffeomorphism group and the gauge group. And then finally, the Hamiltonian constraint makes you do a further Poisson reduction down to this physical phase space, which is what we're really after. Okay. Now, let me tell you let me give you a sort of executive summary of how well we've done on quantizing gravity with this setup. So, in an executive summary, the executive doesn't want to know all the details, they just want to know the bottom line. So that's what I'm going to give you here. So I should be using a PowerPoint presentation at this stage here, but I couldn't afford it. So we have, at the classical level, these three processes of Poisson reduction that I described on the previous transparency. The third one, the Hamiltonian constraint. That's the killer, okay? That's the one that does not have a nice description in terms of three-dimensional geometry. That's where all the real meat of the time evolution and Einstein. Yeah, that's right. That's right. So, well, this is a cotangent bundle, and as I said, in the typical way to quantize that and get a Hilbert space is just to take L2 of the base space. Well, we don't know what L2 of the space of connections is. However, last time I showed you what L2 of this slightly bigger space, a kind of completion of the space of connections, I showed you what that is. So L2 of A bar is well defined, so we do know how to quantize this. Here, similarly, we do know how to quantize it. It's a cotangent bundle, and we do have a measure, not on the space of connections mod gauge transformations, but on this completion that I described last time. So this space here is the space that has this basis of spin networks.
So this is like begins at quantized, but when you have this, you feel it's more or less quantized?
We have a well-defined Hilbert space. We have a whole bunch of operators on it corresponding to interesting observables over here.
That's all part of it.
And so, yeah, right. I'm going to talk about those operators. Yeah, well, right now I'm just sort of giving you the Hilbert spaces, but right, you're not really done until you know how all sorts of things you're interested in the classical theory correspond to things in the quantum theory. So there's a lot of stuff there. Right. Then, this diffeomorphism constraint, we do know how to deal with. We don't know how to deal with it directly. This space is a little bit too hairy for us, I think, so far, to know what L2 of it is. So this route we haven't done. Don't know how to do, but we do know how to mod out by diffeomorphisms over on this side of the story. So here, there's a basis given by spin networks, these embedded graphs sitting in space labeled by things. And here, basically, it's sort of what you might expect. It has a basis given by diffeomorphism equivalence classes of spin networks.
Non-invariance.
What?
Like non-invariance.
Non-invariance, right. So this is so right. So that's why it's at that point that people realize, hey, non-invariants have a chance of giving us states of quantum gravity. Certain non-invariants will give you elements of this space, or more generally, spin network invariance. Yeah.
So you want some of this diffeomorphism invariant? We started out yesterday with this real analytic type of stuff. So is that why you need to eventually develop the smooth aspect of it?
Yeah.
It's real analytic you did.
Well, if you mean real analytic diffeomorphisms, then you can use the real analytic thing. But if you really want all smooth diffeomorphisms, then you need to ponder the smooth situation, which is why we did that. Yeah, that's right. Yeah, and so you could do this all in a piecewise linear context too, and then you can do something else. And as you might expect, things get tough right when you think you're beginning to succeed. So here, Thomas Thiemann has proposed a formula for the Hamiltonian constraint. That is the operator whose kernel would be a collection of operators whose common kernel would be this physical Hilbert space, the long-sought Hilbert space whose vectors describe states of quantum gravity. However, that Thomas Thiemann. So this was actually a while ago. I guess maybe in 96 or 97?
78.
What?
97, 98.
97? 98? Okay. So he came up with an explicit proposal for well-defined operators on this space whose kernel would be here. And he even started studying what their kernel looked like. That is controversial, partially because it's very difficult to come up with enough tests to see if such a proposal is right. Eventually, you want to make physical predictions of some sort and see if they, even if you can't test them experimentally, you'd like to see if they make some sense. But it's very difficult to squeeze predictions out of this Hilbert space until you know some observables on it. But those observables would have to be observables that are invariant under all diffeomorphisms of space-time, and that's where this problem of time comes in. Yes?
I'm just wondering, just to get an idea of where this stands, can this formalism, can you find some semi-classical domain where you can reproduce Newton's law?
People are busily... Can you find some semi-classical domain in which Newtonian gravity emerges as a kind of limit of this? Well, unfortunately, we don't know quite how to do that yet. We're busily working on that. There are actually lots of people coming up with things like coherent states, which would be approximations to flat geometries. And yeah, so we're working on it. It's tough.
Right? Doesn't it worry you that...
Oh, it worries me. Jesus Christ. What do you find? No, I mean, I'm sort of betting my life that this will work.
Why worry?
Yeah?
Of course, and this is a fundamental question, right? I mean,
He's also betting his life that this will work. He's even more worried.
no, I'm not betting my life at all. But I think the situation is the same thing with, in every approach. In string theory, for example, in string theory, for example, the problem is really that one uses supersymmetry. One has higher dimensions. We look around us, there is no supersymmetry, there is no higher dimensions. And so one needs ideas about how to come down to our... Okay, we should talk about it.
Yeah, I don't want to get into an argument about the relative merits of different approaches right now. All approaches have their problems, and we can argue all night about which ones are worse. Yeah?
So is the difficulty actually defining the Hilbert space each is, or is it the analog of the Cosmology reduction?
No. This is the difficulty in defining this Hilbert space, or is it in the Poisson reduction? So the real difficulty is neither of those things. So this Poisson reduction is perfectly fine. Tiemann has defined this Hilbert space to be the kernel of a whole bunch of operators on this space. Of course, that sort of definition is a little bit indirect, but he's also, in fact, found some explicit elements which are in the kernel. But, while we're at it, nobody knows a direct route from here to here, which would help us feel we understood what's going on. But the real difficulty is none of those things. It's that you can imagine various alternative approaches to what Tiemann did, and to decide which one of those is right, we need to come up with some tests which are of a physical nature to see whether they're right. And that's what people are busy working on. And I should emphasize that's what Abai, among other things, will talk about in his talk tomorrow. So in the context of cosmology, you can consider somewhat simplified models along the same lines. And Martin Boyewald has taken Tiemann's ideas on the Hamiltonian constraint and applied them to quantum cosmology, that is the study of the very early history of the universe at the point when quantum gravity effects would have been important, and has gotten some very interesting results. So I'm not trying to say that we're like completely in the dark about how to go about testing Tiemann's ideas, but it's a major, difficult problem.
So this ties in with Martin's question, right? You carry out the program, you suggest that would be another.
That would be another test, yeah. People are also working on that. Right now, I think the most exciting tests so far are these cosmology ideas. I'm not betting my life in the sense that I'm going to commit suicide if it doesn't work, but it doesn't mean that I'm wasting lots of time if it doesn't work. Oh, yeah, okay, that's true. This conference is a lot of fun. It just depends how serious you want to be about these things. Okay, so let me now talk about Hilbert spaces for quantum gravity. So I listed various ones on the right-hand side of that previous transparency. The one that I've explained the most about last time was this L2 of A bar mod G bar. So I showed you last time that this has an orthonormal basis given by spin networks, which are these graphs embedded in R3 manifold representing space with edges labeled by representations of SU2, or in other words, spins, and vertices labeled by intertwining operators. If they're all trivalent vertices, you wouldn't need to bother labeling them because you can just pick a canonical one. Here's a 4-valent one, so I need to label that. So that's a nice space. And similarly, as I said, this diffeomorphism invariant Hilbert space has a basis given by diffeomorphism equivalence classes of spin networks. But to understand any of these spaces, what we need to do is come up with some nice operators on them which correspond to physical observables, things you might want to measure. What? Embedded in a three-dimensional space. Oh, yeah. That's one of the things that's great about it. It winds up being connected in lots of interesting ways to the kind of things that Dylan Thurston was talking about yesterday and lots of people have worked on. That's right. That's a promising...
It's not just exactly
it is exactly that, yes. Yes. That's what's great. That's what's great about it. There might be some interesting things we can do using that. At the at this level, it's not modulo isotopic. Here, it is. We've modded out by diffeomorphisms here. Diffeomorphism is a space connected to the identity diffeomorphism. So, well, I'm mainly going to talk about this, but many of those results turn into results about this. So it really is related to.
So it's a countable space. It's separable space.
It's not separable if you have vertices of high valence because you have moduli of types of intersection modulo diffeomorphisms. If you restrict, if you restrict yourself in various ways, yeah, or if you were restrict to like a piecewise linear context where you can wiggle those things around, then it becomes separable. That's one of the things I like about the piecewise linear setting. Okay, so we'd like to come up with some operators on this space, which what physicists would call gauge invariant observables. And so the idea is that functions on our cotangent bundle of the space of connections mod gauge transformations should get promoted in some manner to operators on this Hilbert space. And there's a standard recipe for doing that, which I already sketched in the case of the point particle on the line. Functions of position get turned into multiplication operators. Function of momentum get turned into differential operators. Here, the analog of position is the A field. The analog of momentum is the E field. So you can hope that gauge invariant functions of this connection will act as multiplication operators, and some of them indeed do. These operators of this sort, depending on this connection, will tell you information about what parallel transport does. And the most famous and original example is a so-called Wilson loop, where you pick a loop in your space and you write down this function of a connection. You just take the holonomy of the connection around the loop. You say, evaluate it in your favorite representation. I like the fundamental representation of SU2, that is the spin 1/2 representation, the two-dimensional representation. So I'll get a 2x2 matrix there and take the trace. That will be a gauge invariant function of A. That's called a Wilson loop, and it's been used for a long time in physics to study gauge theories. So multiplication by this function will act as an operator. In fact, prove it's a bounded self-adjoint operator on this Hilbert space. And so those operators are measuring information about what is...
This is before you divide by diffeomorphisms.
Right, I'm not going to mod up by diffeomorphisms in this talk just because it sort of makes everything a little more complicated. So, but this is right. We're not modding out by diffeomorphisms anyway here. These are a specific loop in a specific place in space. So there's a nice little theorem you can show, which is, first of all, finite linear combinations of spin networks form an algebra under pointwise multiplication. So they're functions on A bar mod G bar, these spin networks. And you can multiply them. And actually, if you have two spin networks that share the same graph, multiplying them just corresponds to tensoring the representations, the way Dennis was mentioning last time, tensoring the intertwining operator. So it's very nice. And the nice part of the theorem is that in this case, that algebra is generated by the Wilson loops. So you can write every finite linear combination of spin networks as a linear combination of products of Wilson loops. These guys are dense in L2 of A bar mod G bar. So you can understand this whole Hilbert space in a nice way by looking at products of loops. And that's why I got so interested in Dennis's talk, where he was describing all these interesting operations on collections of loops. So I bet a lot of those operations will turn into operations on this kind of Hilbert space, if I'm smart enough. And that's exciting to me because his operations wound up getting indexed by Riemann surfaces, which is string theory. Anyway, there are also even more interesting observables which come from functions of E. So the gauge invariant functions of E you would expect to act as operators, differential operators, or more generally pseudo-differential operators on the space of functions on A bar mod G bar. So heuristically, just like momentum gets turned into the operator 1 over I ddx when you're studying the point particle, you expect that that E, when it gets promoted to being an operator on this space, or actually on L2 of A bar, would be 1 over I times this functional differentiation with respect to the connection. So using that heuristic recipe, you can in fact turn various functions of E into well-defined operators on this space. And those operators, they're capturing information about the frame field. And if they're gauge invariant, that means they're capturing information about the metric, because the metric is what's left when you take the frame field E and mod out by gauge transformations. So there are various examples that have been worked out by Ashtekar, Lewandowski, and other collaborators. So they're volume operators associated to any open set in your three-manifold. There's an operator that measures the volume of that region. I won't talk about those, but I'll talk about something similar. There are also area operators which measure the area of any surface in your three-manifold. So let's talk about those. So if you have an oriented surface, sigma, sitting inside your three-manifold, first of all, you can figure out how to describe its area classically. That is, how you can describe it in terms of the A and E fields at the classical level before this quantum stuff shows up. Well, it turns out that the area of the surface is basically just the integral of the square root of E dot E. That's a somewhat scary-looking expression if you're trying to remember what kind of a thing E is. E was... One way to think about what this E field is it's two forms taking values in add P. So you can write E out as an add P valued function times a 2 form, and then this expression here makes sense. You just take the add P valued function, you take its norm squared, square root it, and pull the 2 form outside. That's the sort of thing you can integrate over a surface. So this is a formula for the area of a surface that you can derive from the more traditional formula for the area of a surface in terms of a metric.
This makes sense if C was not non-degenerate.
Yes, it makes sense even when E is degenerate. It could be 0, for example. That's the funny kind of thing that can happen. That's why we're extending general relativity to certain degenerate situations. Right, it could be 0. So the idea of how we're going to quantize this, that is, turn this into an operator on L2 of A bar mod G bar, is that we grab one of these formulas here and we attempt to do this substitution where we replace the classical E by this operator here. There are varying levels of rigor with which you can attempt to do that, but I'm not going to even try to sketch how it's done. I will just more or less jump to the result. because that's actually the interesting part. So let me just tell you, I'll give you a heuristic explanation of why we're getting this result, but I'm not really giving a derivation, although one can.
The result will make sense. The operator will make sense.
It'll be a, yeah.
You're just saying the justification of it, that's more or less opposed.
There's a very good justification of it, but I'm not giving it. Yeah. So I'm going to give you the result, which is so intuitively plausible and nice that that it's better than giving the derivation. So to understand this area operator, I'm now writing a little hat on the A to denote that now we have an operator on L2 of A bar mod G bar. To describe this thing, I'll describe its action on the spin network states. So suppose sigma here is a surface and psi is a spin network. Well, there are various kinds of things that can happen. I'm going to...
That's that thing that's shaped like a kidney with one arc across it, that's what psi is.
Yeah, that's what psi is. Psi is what they call a theta net. So psi is just some spin network that looks shaped like that with 3 different spins on its edges there. Yeah. Yeah, I had the surface shaded when I wrote it down with the Xerox. Didn't catch that. So, well, this is not a derivation. This is a heuristic sketch of how we get this result. So we would like to know what happens when we apply this area operator to this state. Naively, you'd expect you just write down the same formula that we had classically, but now stick in E hat. Well, E hat, remember, was functional derivative with respect to A. And, well, this, as I said, it's going to be heuristic, so I just have to relax and give it here. So the functional derivative with respect to A acts as one of these left invariant vector fields on the group. Which group? The group that describes all the possible holonomies along one of these edges that goes through the surface. So what you expect this thing to turn into is none other than the Casimir operator on the group. That is the Laplacian on the group. The eigenvalues of that Laplacian on the group are just these numbers, the square root of j times the square root of j plus 1, where j is the spin labeling the edge that pokes through the surface. I don't know if that made sense, but that's a heuristic derivation of this result here. So what we get is that in this case, when we have a spin network poking through a surface transversely, it will be an eigenvector of the area operator with eigenvalue given by a sum over all edges which poke through the surface. And actually, not just the sum over all edges, it's the sum over all the points at which the edges poke the surface. A given edge might poke the surface more than once. You have to count each of those punctures separately, and you add up for each one a factor of the square root of j plus 1, where j is the spin labeling that edge.
So you'd have 2 times 3, square root of 2 times 3, given twice.
Right, so we got square root of 2 times 3 for here, square root of 2 times 3 for here. So 2 times the square root of 6 is what this number is in this particular case. Yeah. So an interesting thing, which I failed to emphasize, but is utterly crucial, is that the Emirtsi, or Barbero-Emirtsi parameter gamma shows up in here, because it showed up in the relation between the E field and the metric. It was around in the last transparency as well. So this, you see, is where it really matters. This parameter gamma is affecting the eigenvalues of area operators. So the moral of the story is that we can understand the physical meaning of these spin network edges. We've already seen last time that in electromagnetism they represented field lines of the electric field. Here they're representing field lines of this E field, which is analogous to the electric field, but it's really the frame field. So it's as if the frame field is 0 everywhere except along these curves, where it's singular. And each one of these curves will give a contribution to the area of any surface that it pokes through. So you should really think of it as if the metric is 0 everywhere except along these field lines where it's singular, infinite, in such a way that we compute the area of a surface as a sum over the places where these edges poke through it. So physicists will call them flux tubes of area because they're used to other situations where various kinds of fields will organize themselves up into little tubes. Like, well, there are things called type 2 superconductors where the magnetic field likes to form little tubes. And this is analogous to that in a sense.
Can you remind us why the labeling on the edges is going to have the corresponding E field, not the A field? That's what you were saying.
Yeah. So I'll give a very sketchy explanation. So associated to each edge, remember we had a copy of L2 of G. When we turn this thing into an operator, we could ask, how is it going to be acting on that particular copy of L2 of G if the surface gets cut through by this edge? And the way it acts is just as the Laplacian. Because this is really, well, there's a summation over indices here. So this really is what would turn into a second-order invariant differential operator. There's only one such thing on this group. That's the Laplacian on the group. The eigenfunctions of the Laplacian are just these matrix entries associated to irreducible representations of the group. Remember I told you last time there's this Pater-Bile theorem that describes this thing. And that Pater-Bile theorem, if you think about it harder, actually tells you what the eigenfunctions of the Laplacian are. And so you can work out those eigenfunctions, and it turns out that the eigenvalues are just these, the square root of j plus 1, associated to the different irreducible representations which are showing up in the Pater-Bile theorem. So here we have the Pater-Bile theorem. It's giving us something like this, where we're summing over spins j. All the elements of this little vector space are eigenfunctions of the Laplacian with this, well, the stuff inside as the eigenvalue. Then we're taking the square root. So that's a sketchy explanation of where that number is coming from.
Could you take this to be a definition of the quantum area?
Sure, yeah, you can also do that. Right. So quantization is, as I said, it's a lot like cooking. And if the dinner tastes good, shouldn't ask too much about how it was prepared. Okay, so we found a number of things from this. We found that spin network edges should be thought of as field lines of the E field, or flux tubes carrying area. And we've also found what the quanta of area are. That is what some eigenvalues of the area operator are. The smallest non-zero one that we can get is if we stick j equals 1/2. If we stick j equals 0, we just get 0. If we stick j equals 1/2, we get this. I'm now restoring all the units that I've mercifully been hiding all along. There's 8 pi times Newton's constant, the gravitational constant, times Planck's constant divided by c cubed, was secretly being set equal to 1 in all the calculations thus far. And there's the Amirzi parameter. So what we get is this. All these quantities, the gh bar over c cubed, that actually works out to be the Planck length squared. There's a way to construct a length scale from gh bar and c, and that's the Planck length. But the Planck length squared is gh bar over c cubed. That is called the Planck area. So we're getting this funny number, square root of 3 times pi times gamma times the Planck length squared, which is a very small unit of area, 3 times 10 to the minus 70th square meters. So this theory is predicting that area comes in discrete units of about that size. And you'll notice something mildly upsetting, namely, there's an undetermined parameter, gamma, in here, this Barbero-Amirzi parameter. So another thing Abhay will do is talk about a method for trying to calculate what that parameter gamma is by thinking about the entropy of black holes. So I think he'll maybe tell you what gamma is, or at least what our theory is of what it is. So in addition to the in addition to the fact that we have this discrete spectrum of area, we also have non-commutativity of area operators, which I'll briefly sketch to you. So this you can notice when you consider more tricky non-generic situations. For example, suppose you had a spin network that had a vertex lying right on the surface whose area you're measuring. Well, I need to tell you the rule for applying the area operator to this thing. Well, it's a very simple rule. What you do, of course, that vertex, here it's a 4-valent vertex, needs to be labeled with an intertwining operator. I described last time a recipe for describing these intertwiners, and the way you can do it is you just draw an imaginary little circle around that vertex and imagine expanding it out into a trivalent tree, like this, for example. Here we really want to do it like this, not the other possible way. And choices of spins J5, that is irreducible representations of SU2, will determine intertwining operators. So you get a basis of intertwining operators by picking various values of J5 here. And then it turns out that if you take that as your intertwining operator, the spin network will be an eigenstate, an eigenvector of this area operator, with the square root of J5 plus 1 coming in as the eigenvalue. And I've gotten rid of all these units here. So the idea is basically you just take this non-generic situation and you turn it in, imagine turning it into a generic situation by pulling this apart like that. I mean, that's a heuristic rule for remembering what the result is. But now, suppose we had two different surfaces intersecting at this vertex. So let's imagine two surfaces, sigma and sigma prime, which are oriented in different ways, as I've shown here.
Actually, you might say, what do you do after you make this replacement? And you
Oh.
imagine the point that you imagine it transferring to you.
Then you can figure out what the area operator does. This is the punchline here, right? So if psi was labeled with an intertwiner like this, then psi would be an eigenfunction, an eigenstate, whatever you call it, with that as the eigenvalue. And since these form a basis of intertwiners, then we know what the area operator does in general.
If you moved a little up and you had 2 points of J1 and J2, it would be the same answer.
No, then it would be the square root of J3 times J3 plus 1 plus the square root of J4 times J4 plus 1. So that would be different. If you move up or down, you'll get a different answer in general.
The distance of the intertwiner doesn't make this come out to be the same.
No. J5 has to be smaller than, it has to lie somewhere between J1 plus J2 and the absolute value of the difference. And ditto for here. But it could...
So the J5 is the choice of transversality.
Yeah, there's a kind of choice of intertwiner going on there.
Why shouldn't this be kind of
Yeah, it's geometry. If you tweak the surface a little bit, you expect its area to be different, and so it is. This situation. So now I'm considering two different surfaces, sigma and sigma prime, and the same spin network, of which I've only drawn a little portion, the relevant portion. Well, almost the same spin network, but different intertwiners, iota and iota prime, labeling this vertex. Up here, since I want the calculation to be simple, I will pick an intertwiner like this, just like I did in the previous transparency, and we see that then this spin network with an iota on it will be an eigenvector of the area operator, whose eigenvalue involves the square root of J5 times J5 plus 1. Over here, with this other surface, the calculation will work most smoothly if I pick my intertwiner to be of this form, going across, with some spin labeling this imaginary edge, which I will call J6, and then we get the same story there. But now the interesting thing is, here we found a basis of eigenvectors of this operator. Here we found a basis of eigenvectors of this operator, but they're different bases. So this marvelous 6J symbol rears its head again. There's a change of basis matrix that tells you how this basis of intertwiners is related to this basis. And then all we need to know about it is that it's a non-trivial matrix. It really is changing a non-trivial change of basis. So in other words, these two operators have different bases of eigenvectors. They can't be simultaneously diagonalized, so therefore they must not commute. So that's a very fascinating phenomenon. When you have two surfaces that intersect, their area operators don't commute in this formalism.
You're saying we could just forget everything else and put ourselves in this context. Imagine doing these graphical calculations, and this would give us a feeling of quantum.
Yeah, that's
mathematics or quantum, whatever.
That's right.
All the mathematical components.
Yeah, I think if there's any one thing that everyone working on quantum gravity agrees with, it's that when we finally get to a quantum description of a situation and want to work with that, we should sort of leave the classical inspiration behind, except for when we want it, and focus on what we've got more than how we can manage to get there. That's right. So it's only in our tentative fumbling steps towards a quantum theory that we make heavy use of classical ideas. But here we have a quantum theory, and you can treat it on its own terms and ignore how we got these operators if you feel like it. I mean, it can also be useful to take the other approach. Okay, so I'll stop here. Thanks.
Any other questions?
What do you do with these operators if you're looking at these spin lengths up to isotopes? Then you don't have them in a precise place.
Right. Right.
How do you deal with that?
So I've been muttering about the problem of time now and then, and what you're talking about is the problem of space. So in other words, if we're trying to describe things in a spatially diffeomorphism invariant way, you can't specify a surface just by saying it's the xy plane. And so we can't do quite what we've done here. So one approach to that problem is the general approach to that problem that you can implement in various ways is that you want to somehow describe these surfaces whose areas you're trying to measure by physical stuff in the theory rather than by coordinates. So one way to do that is to introduce extra fields into the theory besides the gravitational field, and then talk about the surface where some field has some value or something like that. So people have implemented various proposals for doing that type of thing. But you have to do something like that. You have to locate your measurements relative to actual physical objects if you're trying to talk about things in a diffeomorphism invariant way. And that's, of course, that's perfectly sensible because that's what we actually do. We don't measure the area of a surface that's defined by some coordinate system that God laid down on the world. We measure the area of a surface that's like the sheet of paper or something that actually has some physical existence or connection to physical objects. It's difficult to make that formal, but we have to do that somehow eventually.
You can say the discussion on this transparency is so different than a discussion of quantum geometry.
Yeah.
That's not quantum gravity yet.
Yeah, this could be called quantum Riemannian geometry, yeah. And we're seeing that it's different than the classical Riemannian geometry in various ways, such as the introduction of non-commutativity. Right. But we really haven't brought in Einstein's equations into this at this level of the discussion.
Any others?
Thanks.